All right, today we are pulling back the curtain on a tool that shows you what your machine learning model is really doing. We're going to be talking all about ROC curves and AUC. These are the metrics that unmask the true hidden power of your classification models. So let's dive right in.
First things first, I've got a question for you. Let's say you build a model and it's 99% accurate. That's fantastic, right? Job done? Time to celebrate? Well, what if I told you that 99% accuracy could actually be hiding a model that's a complete and utter failure?
That's right. So in this first part, we're going to explore those exact situations where relying on accuracy isn't just a little bit misleading. It can be downright dangerous.
You see, accuracy really shines in a kind of perfect, balanced world, where you have an equal number of examples for each class and every mistake your model makes costs the same. But the real world is messy, isn't it? It's often imbalanced and the stakes are high, meaning one type of error can be a whole lot worse than another.
Just think about it for a second. Imagine a rare disease that only affects 1% of people. A model could be 99% accurate just by being lazy and predicting no disease for everybody. But that model is totally useless, right? It fails the very people it's supposed to help. Or think about missing a cancer diagnosis. That's a catastrophic error. And on the flip side, flagging every single credit card purchase as fraud? Well, that would be an absolute nightmare for users. The consequences in these cases are huge, and simple accuracy just doesn't capture any of that nuance.
Okay, so if accuracy has these massive blind spots, what do we use instead? Well, we need a way to measure the trade-offs. And this brings us to two really important rates that help us weigh the benefit of getting something right against the cost of getting it wrong.
And it all starts right here with something called the confusion matrix. It's just a simple table, really, that sorts all our model's predictions into four neat little buckets: the stuff it got right and the stuff it got wrong, broken down by what the real answer was. And from this simple table, we can calculate our two crucial rates.
First up, we have the true positive rate. You might also hear it called sensitivity or recall. Just think of this as the benefit. It asks a simple question. Out of all of people who actually had the disease, how many did our model correctly catch? Obviously, we want this number to be as high as possible.
But like with everything, there's a trade-off, and that's the false positive rate. This is our cost. It asks, out of all the perfectly healthy people, how many did we accidentally flag as being sick? This is our false alarm rate, and we want to keep this number as low as we possibly can.
So now we have a benefit, and we have a cost. But how do we see the relationship between them? How do they balance each other out? Well, that is exactly where the ROC curve comes in. It's this brilliant graph that visualizes this trade-off perfectly.
And the idea behind it is actually pretty simple. On the y-axis, the vertical one, we plot our benefit. That's the true positive rate. And on the x-axis, the horizontal one, we plot our cost, the false positive rate. The curve that gets drawn shows us, at a glance, exactly how many false alarms we have to put up with to get a certain level of benefit.
So how do we actually build this thing? Imagine your model gives every case a score, right? Like a probability. We start by setting a super high bar. We only flag things we're absolutely certain about. This gives us our first point on the graph. Very few false alarms, but we also miss a lot of real cases. Then we start to lower that bar little by little. And as we do, we start catching more true positives, but of course, we also trigger more false alarms. Every time we adjust the bar, we add a new point to the graph. Connect all those dots and boom, you've got your ROC curve.
And the shape of that curve tells you pretty much everything you need to know. A fantastic model will have a curve that bows way up towards the top left corner. That's the sweet spot. High benefit, low cost. A completely useless model? That's just a straight diagonal line. It's no better than flipping a coin. And hey, if your curve ever dips below that line, well, something has gone very, very wrong.
Now, looking at a curve is great for getting a feel for your model. But sometimes you just need one number, a final score, something you can use to compare different models head-to-head. And that's exactly what AUC is for.
AUC literally just stands for area under the curve. It takes that whole two-dimensional space underneath your ROC curve and squishes it down into a single score, somewhere between 0 and 1. Think of it as a summary of your model's total power to tell the positive and negative classes apart across every possible threshold.
So let's say you run the numbers and you get a score like this, 0.92. What does that actually mean? Is that good, bad, somewhere in between?
Well, as a rule of thumb, an AUC above 0.9, like our 0.92, is considered excellent. Anything in the 0.8 range is still pretty good. But once you start dipping below 0.7, your model's getting a bit weak. And if you see 0.5, well, that means your model is literally just guessing.
You know, here's maybe a more intuitive way to understand it. An AUC of 0.92 means that if you picked one random positive case and one random negative case from your data, there's a 92% chance that your model will give a higher score to the positive one. It's a really direct measure of how well the model separates the two groups.
Okay, we've gone through the theory, we've looked at the curves, we've talked about the scores. Now, let's bring it all home and talk about why this is so incredibly important in the real world.
I mean, just look at these fields: healthcare, finance, cybersecurity. The stakes could not be higher. A model's ability to tell good from bad, sick from healthy, fraudulent from legitimate, it's not some academic exercise. It has massive real-world consequences. And that is why ROC and AUC are the absolute gold standard for making sure these critical models actually work.
There's a saying that I think just sums this whole thing up perfectly. Accuracy shows surface performance. ROC AUC uncovers true model capability. Accuracy just gives you that one shiny number on the surface, which, as we've seen, can be super misleading. ROC and AUC let you dig deeper to see what your model is truly capable of.
So if you take away one thing, let it be this. Instead of just trusting a single, often flawed number like accuracy, these tools give you the full picture. They show you the trade-offs your model is making, which lets you make a much smarter decision about which model is really the right one for your problem.
And that really leaves us with one final, critical question to think about. If you've only been looking at accuracy up until now, what hidden flaws, what dangerous trade-offs might a ROC curve reveal in your own models?